Okay. So, we have been discussing this issue of random sequences, that is just for a recap. We initially started with just one random variable and function of one random variable, then two random variables, then one function involving two random variables and two functions involving two random variables. Here we tried to generalize that to a set of n random variables which are ordered as a sequence x 1, x 2 up to x n, and we first consider one function of such n random variables and then n functions of such n random variables, right. So, there are several issues which we did not discuss last time. They are all just analogous to those issues which we considered in the case of two random variables, say. Okay. So, we will just continue from where we left last time. Okay. But just one remark, we have so long used real valued random variables, okay. But random variables could be complex valued also. So, suppose we have got this suppose z 1 is x 1 plus j y 1 dot 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 up to say z n x n plus j y n. So, z 1 to z n, we have got a set of n complex random variables, right. But remember, each of these z 1 to z n, they have got two components, one is the real component and another is the imaginary component x 1 y 1, and now x 1 also is a random variable, y 1 also is a random variable. Similarly, x 2 is a random variable, y 2 is a random variable. So, a set of n complex random variable equivalently means a set of twice n real valued random variables, which means probability density of z n is same as actually a probability function, probability density function of two n variables x 1 y 1 x 2 y 2 dot 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 x n y n. Okay. Further, if z 1 dot 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 z n, they are independent, then it means that p x 1 y 1 dot 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 x n y n, that will be like this, which stands for the probability density for z 1, because z 1 has the two random variables, real valued random variables x 1 and y 1 in it. Then p x 2 y 2 dot 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 p x n y n. Okay. Then again, suppose we have got a single function g x, x is a vector. Basically, x means actually is a function of n random variables x 1, x 2 dot 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 x n. Okay. Now, by extending our previous argument, we can then say that expected value of g x is nothing but times the corresponding probability density function dx 1 dot 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 up to dx n. Okay. Obviously, if instead of this real variables x 1, x 2 up to x n, we had a set of complex n number of complex valued random variables z 1, z 2 up to z n, then instead of having a n fold multiple integral, we would have had a twice n fold multiple integral, okay, and the probability density function would have been, I mean, this is g z 1 up to z n, and probability density function as before would have been p of x 1 y 1 x 2 y 2 dot 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 x n y n, and we would have had dx 1 dy 1 dx 2 dy 2 dot 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 dx n dy n, just that generalization. Also, as before, you can see that there is a linearity that is valid here also, that is expected value of say sum of functions C 1 G 1 x say plus C 2 G 2 x is same as C 1 expected value of G 1 x plus C 2 expected value of G 2 x, and instead of having just two terms, you can also have n number of terms. So, the linearity works. Okay. Then given a set of complex valued in general, because now I wanted to be more general. So, complex valued random variables say x 1, instead of z 1 I am calling them x 1 now, x 1, x 2, x n. Then covariance we now define first so E of x 1 says mu 1 or E of x k is mu k, where k goes from 1 to up to n. That is x 1 has a mean value mu 1, x 2 has a mean value mu 2 dot 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 x n has a mean value mu n, and then we define covariance between say x I and x j as expected value, you can call it you can call it C I j is expected value of x I minus mu I times, now the difference x j minus mu j and then complex conjugation here. Earlier we have dealt with similar things, but since that time we were dealing with only real valued complex variables, we had a more simplified expression for this covariance where there was no complex conjugation, but in a more general case this is the definition of covariance. Why this complex conjugate is necessary, you know, simply because if you now are interested in the variance of say x I, okay, say variance of x I. Now, we all know that variance denotes power, expected value of the power, okay. That is average power. So, average power has to be real and non-negative. So, if you put a star here, that will make the variance, that is expected power, real. How? You can easily see variance of x I equal to say sigma I square is what? Expected value of x I minus mu I times again x I minus mu I star, which makes it this. Because a complex number and its own conjugate multiplied gives us to the mod square, and as mod square means it is a real function, right. It is happening because of this star. Okay. So, this is a variance, this is a covariance. Okay. As before, this covariance expression you can simplify like before. I repeat again here, our C I j was, I am just repeating, You can now break it up. One term is E x I x j star, okay, then minus mu I E this cross term x j star minus mu j star E x I plus mu I mu j star. Now, you see we have got a quantity like expected value of x j conjugate. What is that? Okay. Now, we know that we can write x j conjugate as a function of x j. Given x j, this function evaluates its conjugate. So, x j star is a function of x j, which means this implies expected value of x j star is nothing but expected value of g x j, and we have already seen this is nothing but g x j times p x j d x j, right. And then in the integral g x j is x j star, I replace this by x j star, p x j is a real quantity. So, you can also write this like minus infinity to infinity x j p x j d x j and then star. That is, first you replace d x j by x j star, but you see that the other quantities, that is p x j and d x j, they are real valued. Okay. So, you can take the integral, you can do the integral first and then conjugate. Okay. And what is this integral? This is nothing but expected value of x j, that is mu j, okay, that is mu j star. Okay. So, I will use this fact here. So, I continue. This is as before E x I x j star. In fact, this is called the correlation minus mu I, and we have seen a while back this is mu j star and then minus mu j star mu I plus again mu I mu j star. So, essentially it becomes E of x I x j star minus, after simplification we only have one mu I mu j star, which means E x I, which is mu I, and E x j star, which is mu j star, which means this implies if x I and x j are uncorrelated, then as before C I j is equal to 0, meaning E x I x j star is simply E x I E x j star. Okay, either you can take x j star and then expected value of it, or E of x j then conjugate, either it is the same. Okay. As an example, suppose you have got, and one more thing, if x 1 to x n they are statistically independent, then obviously P of x 1 dot 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 x n is nothing but P of x 1 into P of x 2 into P dot 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 P x n, right. Now, suppose we are giving this that x is okay, E of x k is mu k, and the variance E of x k minus mu k mod square is sigma k square. Okay. Then firstly, and also x 1 to x k, they are independent. We all know, and it is easily seen here, that if two random variables are independent, they are also uncorrelated. Okay. There is a covariance will be 0. For instance, if you just have doubt about it, you can see that suppose say x I x j as before, x I minus mu I x j minus mu j star expected value. This is the covariance. I am saying that if x I and x j, they are statistically independent, then they are uncorrelated also, means the covariance will be 0. That is easily seen here. After all, if you take the expected value of this, that means you take this quantity as a function of two random variables x I and x j. So, to find the expected value, you have to multiply by its joint probability density function P of x I x j, but since x j are statistically independent, you can write P of x I x j as P x I into P x j, then integrate. So, one integral will be with respect to this x I minus mu I multiplied by P of x I integrated, that will give us to 0, because x I has a mean mu I. Similarly, the other integral also will give us to 0. Okay. So, if they are statistically independent, the correlation is covariance is 0, and we say they are uncorrelated. So, we are given here the fact that x 1 to x n, they are n number of mutually they are n number of mutually independent random variables, which means they are uncorrelated also. Okay. So, then what happens to E of x? Obviously, E of x 1 plus E of x 2 dot 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 E of x n using the linearity. So, it is nothing but sigma 1 mu 1 plus mu 2 plus dot 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 mu n. Okay. And how about the variance E of this, I say mu x. How about mod x minus mu x square? Okay, as we know, x is x 1 plus x 2 plus dot 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 x n. Okay. Which means you can write okay. I replace x by x 1 plus x 2 plus dot dot x n, mu x also by mu 1 plus mu 2 plus dot dot mu n, and then that means you can write it as simply here first x minus mu 1 plus dot 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 x minus mu n, and on the other side x minus again mu 1 plus dot 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 x minus mu n, but star. Okay. and this is x, sorry, this is x1 to xn, x1 to xn. That is, I am replacing x by x1 plus x2 plus dot dot xn, mu x by mu1 plus mu2 plus dot dot mu n. So, taking x1 with mu1, x2 with mu2, xn with mu n. Okay. Now, if you take the product, the cross products are 0, because the variables x1 to xn, they are given to be statistically independent, which means they are uncorrelated. So, the covariance is 0. Only the direct products, that is x1 minus mu1 times x1 minus mu1 star expected value, only that is non-zero, and that gives the variance of x1. Similarly, the other one gives variance of x2 and so and so. Okay. So, that means this gives rise to what? Variance of x1, that is sigma 1 squared, then sigma 2 square plus dot 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 sigma n square. We now consider a very interesting example which uses these concepts. Suppose we are given this is as before x n, which are, you can say, uncorrelated. Mutually. Then define that is simple sample average of this n random variables. Just add them and divide by the total number of variables involved, that is n, and call it, this is a new random variable, call it x tilde. Okay. And similarly defined a random variable, say v, as 1 by n minus 1 times x I minus this x tilde square. Okay. Question is, what is E x tilde equal to what? Then what is the variance? Okay. Just a minute. What is sigma x? Maybe instead of x tilde, it is better to remove the tilde, just because there is no x anywhere. So, I remove the x tilde. So, x is the sample average. Okay, x is the average of those n random variables x 1 to x n, and v is what? 1 by n minus 1 times the summation x I minus that average x, average random variable. Mind you, x also is a random variable. So, x I minus x whole square. Okay. And we are assuming, I forgot to mention, that all the variables are real here. They are all real variables, that is n real random variables. Okay. So, question is, what is E of x, that is this new random variable x, which is formed by averaging the n random variables. What is the expected value? There is a mean value or expected value of x. then what is its variance, sigma x square, sorry, equal to what? Okay. And the other one, what is the expected value of this, what is E v? Okay. I am not interested in squaring it up, because then this term will be raised to the power 4 and it is not of use to me here. So, just what is the expected value of such v, which is some sort of average of squares of what? Deviation of x I from the average random variable. Just take that, square it up, add for all the variables and divide, instead of by n, here I am dividing by n minus 1. So, that is the difference. So, it is not exact averaging would have meant division by n, but here I am purposefully dividing by n minus 1. Okay. So, these two things we have to find out. Okay. First one is very simple. E of x using that linearity, obviously 1 by n summation E of x I okay. And so, E of x I what is E of x I forgot to mention that okay, given for all random variables they have the same mean mu and same variance for all of them. Since they are real valued, I am not putting any mod. So, sigma square. This is given. I forgot to mention this, that we are given a set of n uncorrelated, that is mutually uncorrelated real valued random variables x 1 to x n, where each of them has same mean, constant mean mu and constant variance sigma square. So, that is same for all the random variables. Then by just adding and then averaging, I found a new random variable. My question is, what is the average value of that, expected value of that. Then each random variable is, I found the difference between that each random variable with the average one, take the square, sum and average, not exactly, because that would have meant dividing by n, I am dividing by n minus 1. Then if I form this v, what is the expected value of v? That is the question. So, I first start with expected value of this x, and which is obvious using the linearity and this formula, expected value of s will be 1 by n summation, I can push the expectation operator inside the summation, and E of x I for all I is equal to mu. So, mu times n cancel. So, this will be equal to mu. So, x has the same average, same expected value as each of the random variables has. Okay. Then question is, what is the variance of x? Okay, what is the variance of x? That means there is now have to find out what is this quantity. Mean value of x is mu, we have already seen. So, what is this quantity? Okay. Now, what is x? We know that x is 1 by n summation x I equal to 1 to n, right. And now you replace this x by here. So, that means you can write it like this, E of, you can take 1 by n square summation x I within bracket minus n times mu whole square. Very simple. Replace x by this. I want to take 1 by n outside the bracket. So, it becomes 1 by n square. So, mu gets multiplied by n. Okay. Which means you can take 1 by n square outside because it is not random. Expected value of again x I minus mu, sorry, you can put it this way, x 1 minus mu plus x 2 minus mu plus dot 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 x n minus mu whole square. In the whole square, the cross terms will be 0 as before because of uncorrelatedness. So, this will give rise to just the variances for each of them, and each of them has the same variance sigma square. So, there will be total n times sigma square. So, n into sigma square will come on the top, n square here. So, you get sigma square by n. Okay. So, our second question is answered. Now, the third question, what is, that is, I rewrite again, we formed the variable v as okay, question is what is equal to what. Okay. For that, we already know that mean of x I is mu, mean of x is mu. We first consider this thing, E of what is this, x I minus mu, there is a covariance between x I and x I minus mu and x minus mu, because x I also has mean mu, x also has mean mu. So, the covariance between any x I and x, what is that? Let us find it out. Okay. Now, as before, you replace x by its expression. So, 1 by n summation x I minus mu, 1 by n comes out, and you can write this as x 1 minus mu plus dot 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 x n minus mu. Okay. Once again, all the terms will be 0 except for the case where from here I have got x I minus mu. So, only square of that will remain. Other terms like x I minus mu times x 1 minus mu, expected value will be 0 because x 1 and x I they are uncorrelated, and likewise only when you have got a term x I minus mu from here. So, square of that will come up, expected value, which is nothing but the variance of x I, and variance of x I we all know is a constant independent of I, which is sigma square, right. So, this will become nothing but sigma square by n. Okay. This will become nothing but sigma square by n. Okay. So, we now come to this question, what is E v? So, if we apply E here using linearity, we will have this, and you can write here 1 by n minus 1 and same summation I equal to 1 to n E, but inner quantity you can write like this. Square. Okay. Now, here there will be one term x I minus mu whole square expected value, which will give us the variance of x I, which is sigma square you know. Similarly, another term will be expected value of x minus mu whole square, which is the variance of x. Okay, and we have already seen variance of x also is sigma square by n, and there is a cross term twice expected value of x I minus mu, x minus mu. There is a covariance between x I and x, which is also sigma square by n. We have just now seen. So, if we use those figures here, first is sigma square, then minus twice sigma square by n from the covariance term, the cross term, and then from the variance of the other one sigma square by n. Okay. And this sigma square, now we are summing, there is a summation, right. Though I has gone, there is a summation over n. Okay. So, that means, now what is it? If you take sigma square common, this n times sigma square, if you take common sigma square by n minus twice sigma square by n. So, we are left with only minus sigma square by n, take sigma square common. So, you get n minus 1 by n, and this n cancels, this cancels, you are left with what? Just sigma square. Okay. This is the answer. Few definitions. When the random variables say x 1 to x n, they are independent, we have seen they are uncorrelated. Okay, obviously, same applies for the complex random variables also. For instance, if say z 1 is x 1 plus j y 1, z 2 is say x 2 plus j y 2, and we say that z 1 and z 2 they are statistically independent. That will mean that if z 1 z 2 are independent, this will imply that probability density of z 1 z 2, which is nothing but some p x 1 y 1 x 2 y 2 will be same as x 1 y 1, which goes for z 1 times p x 2 y 2. Okay. And if this is given, then for complex variables also, complex random variables also, they will be uncorrelated. That is, E of z 1 z 2 star will be E z 1 into z 2 star. That is very easily seen. That is, E of z 1 z 2 star will be nothing but z 1 z 2 star multiplied by the joint density integrated, but joint density can be written like this, can be broken like this. So, there will be one on one side, you have got z 1 times p x 1 y 1 d x 1 d y 1, and again z 2 star p x 2 y 2 d x 2 d y 2. Obviously, this will give rise to E z 1 and this will give rise to E z 2 star. Okay. So, that means, I write separately here. We have we see easily Okay. Finally, suppose sorry suppose are independent, that means if you take instead of x1 a function g x1, instead of x2 a function g x2 dot a function g x n, the same as, after all what is this? This whole product is again another function, you can call it g1, sorry, you can call it g2, gn, defined functions. x1 has a function, I mean I take a function g1 which works on x1, then a function g2 which works on x2, gn works on xn, and I consider the product which is basically a function g of x1, x2, xn. Expected value will be what? This product multiplied by the joint density integrated, but if they are independent, joint density is nothing but product of individual or marginal densities. So, you just separate out the integral, one will be with respect to x1, just g1 x1 times probability density of x1 integrated, same for x2, same for xn. So, this will give rise to, first one integral will give rise to the expected value of just g1 x1, then expected value of g2 x2 dot expected value of gn xn. Now, I come to a very important topic, that is correlation matrix and covariance matrix for a set of n random variables, in general complex valued random variables. Okay. That is in general complex valued. Okay. I need to define certain things like what is meant by Hermitian transposition. Okay. Definition: Hermitian transposition. Given a vector x as say x1 dot xn, Hermitian transpose which we denote by x Hermitian, sorry, x Hermitian, this will be given by actually conjugate transpose. You have to take the transpose of the vector and then conjugate all the elements. is not ordinary transposition. Its ordinary transposition means just transpose the elements. Row vector becomes column vector or column vector becomes row vector likewise. But here you have to do one more step, that is conjugate the elements also. Okay. So, x h is nothing but, you can either write x transpose. So, if it is a column vector, it becomes a row vector and vice versa, and then complex conjugation, or equivalently you first conjugate and then transpose. This is called Hermitian transpose, that is denoted by x h. Similarly, for matrices, same for matrices, that is, given a matrix A H is nothing but either A transpose then conjugate, just take the matrix, transpose it, you get another matrix, then conjugate all the elements, or equivalently you first conjugate all the elements, then transpose, either way you will get the same thing. Okay. Also, my notations. If any symbol, any letter has a bar or underscore, then it is either a vector or a matrix. Now, if it is written using capital letter, then it is a matrix. If it is written using lowercase letter, then it is a vector. But both have an underscore that differentiates them from scalars. Okay. One more thing you see, x Hermitian x, this will be what? X is a column vector, so it become row vector transposition, then conjugate it, and this is the original x. So, basically it means mod of x 1 square, then mod of x 2 square dot 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 mod x n square all added. Which is also called norm square of the vector, and this is always greater than or equal to 0 and real. Okay. On the other hand, how about x h? This will not become a scalar. Previous x h x was a scalar number because x h was row vector, x was column vector, so product was a scalar. But now here we have x as a column vector as before, x 1 dot dot x n, and obviously x h will be first is transpose, which is row vector, and then conjugate it. So, x 1 star dot 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 x n star. Okay. Which means we will have terms like this, mod x 1 square, then x 1 star, x 2 star dot 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 x, sorry, I am making a mistake, x 1 x 2 star, then x 1 x n star, then again x 2 x 1 star, okay, then mod x 2 square likewise. You see the first row and second column element is x 1 x 2 star, and second row first column element is just the conjugate of this x 2 x 1 star. Okay, and this works. This matrix actually is called a Hermitian matrix. Just a minute. okay, which means if you have terms like say A11, A12 dot 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 say A1n, if I transpose it, A12 comes here and then conjugate. So, this place will be A12 star, this remains A22 and likewise. Okay. Now, these matrices are Hermitian matrices. Why? But before that, you see one thing, A B Hermitian is B Hermitian, A Hermitian. This is not difficult to see. After all, A B Hermitian means you take A B transpose conjugate, and A B transpose is B transpose A transpose conjugate. Okay, and conjugate of a product means product of the conjugate. You have to take the conjugate on each of them, right. So, that means B transpose conjugate A transpose conjugate, which is nothing but B Hermitian A Hermitian. Okay. Now, previously I considered a matrix of this form, you can call it A. My claim is this is a Hermitian matrix, that is A and its Hermitian transpose, they are same. Hermitian transpose means, you take the transpose. So, I comma jth element, where I is the row, j is the column, on transposition that goes to the j comma ith position, okay, and then you conjugate that also. Okay. So, the after Hermitian transposition, j comma ith position gets filled by the ijth element of the previous matrix with a conjugate. Okay. There is a Hermitian transposition. If after doing so you get back the same matrix, then we call it a Hermitian matrix. Now, you can see one thing, this is Hermitian matrix, because what is AH, what is the transposition? H, right, and AB Hermitian means Hermitian X Hermitian, right, and you can see Hermitian of a Hermitian transpose of a Hermitian transpose, that gives you the original vector. After all, this was a column vector, by Hermitian transposition I mean it is a row vector with conjugates, elements conjugated. Again taking the Hermitian transpose, so it again becomes a column vector and conjugation disappears. So, you get back x, and here as before x h, which is the original vector matrix A. So, a matrix which on Hermitian transposition gives you back itself, then it is a Hermitian matrix. Okay. Sorry. Then suppose you take A11, A12, A13, A21, A22, A23, A31, A32, A33. And what is AH? Transposition will not change the diagonal elements, 1 1 remains in 1 1, only thing is they get conjugated. Okay, Hermitian transposition means A12 comes here with a conjugate and A21 goes here with a conjugate, A31 comes here with a conjugate, A13 comes here with a conjugate, A23 comes here with a conjugate, A32 comes here with a conjugate. Now, if these two matrices are same, then A will be called a Hermitian matrix. That means, firstly the diagonal elements A11 must be A1 star, which means it must be a real valued element. So, the diagonal similarly for A22, similarly for A33. So, for a Hermitian matrix, diagonal entries are real and other entries are conjugate symmetric of each other, like 2 1th element of AH, that is second row first column. This is nothing but 1/2th element of, there is 2/1 of AH is same as 1/2 star of A. So, 2/1 element is this and 1/2 element of A is this. If you put a star here, you get back this element. That means AH, this matrix, its ijth element is nothing but A matrix, its jith element star. This is the Hermitian transposition. Okay. Now, if A and AH are same, that means A21 and this, that is we should have A21 is equal to, A21 should be just the conjugate of this, A12 star. Okay. A31 should be A13 star, because this and these are to be same, and likewise. So, the transposition, the Hermitian matrix ijth element, that means I think I continue from here in the next class, because some more properties are to be discussed. Okay. Because this Hermitian matrices, they give rise to what is called the correlation and covariance matrices. So, that is all for today. We continue from here in the next class, because time is up. Thank you very much. Okay. So, in the last class we are discussing this correlation matrices, and in that connection I talked about what is called Hermitian matrices and Hermitian transposition and things like that. So, today we continue from there. So, just to recall what we did last time, given a matrix say A, we define its Hermitian transposition as AH, okay, which actually is nothing but A conjugate, that is complex, take the complex conjugate of each entry of A and their transpose, which is also equivalent to doing it the other way. First take the transposition of A and then a complex conjugate. Okay. That is very simple. So, if A is not a matrix, but just a vector, say column vector, then its Hermitian transposition is what? You first transpose it, so it becomes a row vector, and then take the conjugate of each element. Similarly, if A is a row vector, then its Hermitian transposition will be a column vector with all the original elements are complex conjugated. Okay. If it so happens, if A is a Hermitian, then A is called a Hermitian matrix.